Okay, so we are going to talk about an integration formula called integration by parts. So integration by parts starts out as the integral of u dv. So these are two separate variables. I'm going to integrate to be u v minus the integral of v du. So what you end up having to do is you have to pick out a u and a dv value to start with, and then you take the derivative of your u value to make it du, and you have to integrate your dv in order to find your v value, and then you plug it in here and integrate this back part. Generally, but not always, you want to make the dv the more complicated part because you're hoping that by integrating you make it simpler. You don't want to pick a super complicated u value because then the du, which is going to go here, would also be a disaster, and you don't want that, okay? You want u to be something that has a relatively simple derivative. Now, often when you integrate using an integration by parts, you can get away with just doing this once, and that'll get you the answer. But sometimes this back half is going to require you to do integration by parts again, and we'll talk about what that looks like. This is sort of like u substitution in that you just need to learn how to pick things out correctly, some of which comes with practice. With u substitution, a lot of times they don't write much down. When you're doing integration by parts, I would suggest writing everything down because otherwise it's hard to keep the u and the dv straight in your head if you're not carefully writing them down, okay? So we're gonna do 5 of these, and then that'll be it. So we've got x, square root of x minus 5 dx. So we're gonna pick out a u and a dv and hope that they fit. So realistically here, your two choices are x and the square root of x minus 5. You don't want to pick the square root of x minus 5 to be your u value because it doesn't get any simpler when you take the derivative of it. If anything, it gets worse because then you'll have a square root on the bottom. So that leaves just x to be your u value. So then here you'll have the square root of x minus 5 and dx. So here when you take the derivative of x, you get 1 and then dx. And then here when you integrate this, this technically requires you to do u substitution. If you need to write your u's and your du's down to do the u substitution, write them down, okay? I'm just going to say them instead of writing them down, partially because of space and things like that. So your u value is going to be x minus 5. Your du value is going to be 1 and then dx. So what you're trying to integrate here is you have u square rooted, so that's u to the 1/2. So then you'll add and flip. So then v is going to be 2/3 times x minus 5 to the 3/2. And I wouldn't tack on the plus c. You just want to stick on the plus c at the end once you've finished integrating. So using the formula, you start with u times v. So that's x times this. Put the coefficient in front. Don't put it in the middle. So you got 2/3 x times x minus 5 to the 3/2 minus the integral of v. But the 2/3 is done, so take it out. du, which is just dx. So then this one doesn't require you to do integration by parts again. It's just your u value is still x minus 5. Du value would just be 1 dx. So then you're integrating u to the 3/2. So you'd add and flip. So this one doesn't change. It's kind of looking like a 5. It's not. Okay, so you've got 2/3 times 2/5, so you're looking at 4/15 times u to the 5/2 plus c. When you're doing the bookwork, watch the bookwork because they'll take out an x minus 5 to the 3/2 as the overall greatest common factor and leave the answers looking super weird. Leaving it like this is just fine. Okay, so general rule of thumb when you are doing integration by parts, anytime you have a natural log of x in your problem, that has to be your u value, or it should be your u value, because the only thing that you know how to do with the natural log of x is take the derivative of it, because to actually integrate natural log of x, which we'll do in the next example, actually requires you to do integration by parts. So this has to be your u value because all you know how to do is take the derivative of it. So if u is the natural log of x, then dv, which is your other part, try and make your u's and v's look not the same, is going to be x squared and dx. So derivative of natural log of x, you have 1 over x dx. V, that means you're integrating x squared. Doesn't require u substitution because it's just x, so you'll add and flip. So then you have 1/3 x cubed, and you'll plug it all through. So you've got u times v minus the integral of v times du. So the 1/3, goofy. When you've got the x third, or not x third, x to the third, and 1 over x, you want to multiply those together. So then you've got x cubed over x, which is just going to be x squared dx, and same thing. That doesn't require u substitution. It's just power rule again, so you'll add and flip. So that won't change. So then you're looking at 1/9 x cubed plus c. All right, third one. So I've already said when you have natural log of x in, that's going to be your u value, and then you look at it and you go, well, there's nothing left. That's not great. You still have to have both parts when you do, sorry if you hear the noise, that's the dishwasher. When you do integration by parts. So the only thing you have left here to be your dv is just dx. So then you'll take the derivative of the natural log of x, which is still 1 over x dx. You'll integrate dx, which would just be x. Fine, because it's like you're integrating 1, so if there was a 3 here, it'd be 3x or whatever. So then you want to use your formula. So you've got u times v, so that's x natural log of x, minus the integral of v times du, so x times 1 over x is just going to be 1 dx, and then you just integrate that, which will integrate to be x. All right, 2 more. Okay, so just like when you have natural log of x, you want that to be your u value. When you have e to the x, usually, but not always, that ends up being your dv value. Reason being is that e to the x, regardless of the number of times that you integrate it, it's not going to be a more complicated function. It's just e to the x. It's going to stay the exact same thing when you integrate it. So then you can worry about simplifying this part, okay? This one, word of warning, is going to be one where we're going to have to do integration by parts twice. So then you'll see what that looks like. So first time around, u value is going to be x squared plus 1. Fine. dv is going to be e to the x. So here we'll take the derivative. Derivative of x squared plus 1 is just 2x. Fine, here we'll integrate. E to the x just integrates to be e to the x, so it does nothing interesting at all. So then you've got u times v. Okay. I'm trying to see how far left I need to start, so I hopefully don't run out of space. Minus the integral of v and du. So the two, not helpful. Okay, so then you look at this part and you go, well, that's not great because there's no good formula for that. So that's how you know you're going to have to do integration by parts again. we need u, and we need dv. So rule still stands. When you have e to the x, that's what you want your dv to be. So that leaves x to be your u value, and then it'll simplify down and things will work out better. So then du is just going to be 1. Here you'll integrate. So then it stays e to the x. Fine. So then you need to plug it through the formula. When you're plugging it through the formula, you need to make sure that you distribute the -2. Some people will have -2, do a big set of parentheses, fill out the formula, and then distribute. That'll work. I tend not to do it that way because it's more writing, and I like to avoid that if I possibly can. So first part won't change. Fine. Now you got to use the formula with this u and dv, not the top one. So then you've got -2, and you have u times v. So then you got x, e to the x, minus, but really because you're distributing the -2, it's +2 integral. And then you've got v, which is e to the x, du, which is just dx. So e to the x still is going to integrate to be e to the x. So then you just got to finish this part and toss your c at the end. And then same thing, that'll be your answer. All right, last one. Sorry, that's supposed to be a square root. There we go. Guess it really didn't matter. I could have put it to another power, but okay. So I think problems like this are interesting because they involve. I always think of it as stealing. So we'll talk about what that looks like. So here, if you're going to pick your stuff. Trying to see how much space I want. Your u value, you would sit there and go, okay, so this will get yucky if I take the derivative. So you would pick x to the 9. Don't write this down. And then your dv value would be the square root of x to the 5th minus 6 dx. So before we take the derivative of this, we're going to talk about how to integrate this. So when you go to integrate this, your u value would be x to the 5th minus 6. And your du value would be 5x to the 4th. And you sit there and go, I don't have x to the 4th, I have dx. That's not great. You need 4 x's. You cannot randomly invent them from space, okay? You can put constants into the problem when you integrate. You can't randomly throw x's in there. They have to be coming from somewhere. So you sit there and go, well, I need 4 x's. So then you look over here and say, but look, I have 9 of them. They don't all need to do this. So then you steal. So you take 4 of them to come and do this job, okay? Which leaves 5 of them over here. And then you treat the problem the way that you normally would. We're just splitting the x to the 9th into 2 pieces so that this integration is legitimate integration and not nonsense. So here when you take the derivative, you end up with 5x to the 4th. So then here when you integrate, u value x to the 5th minus 6. du is 5x to the 4th. We have the x to the 4th. We're missing the 5. You do still need to integrate in a legitimate way. Okay, you can't just randomly do power rule and hope for the best. So you would put in the 5, pull the 5th. This is where, same thing, if you need to write down the steps for u substitution, write them down so that you don't do terrible things. So then you've got u to the 1/2 times a 5th. So you'll add and flip. So you've got 2/3 times a 5th. So 2/15 times u to the 3/2. Fine. So then we'll fill it through. So you've got u times v. So we've got 2/15 x to the 5th times x to the 5th minus 6 to the 3/2 minus the integral of v, and the 2/15 is not helpful. Du. Now this is one case in which I'm going to leave the constant in. The reason I leave this constant in is because it's helpful in that then this is exactly your du value. If you sit there and you go, I don't want to leave the constant in, that's weird, I want to take all of them out and make them stupid and deal with it later, you can. It's not wrong, okay? You could pull out the 5 also and reduce that. Either way, you're going to get the same answer. I only leave the constants in if they're helpful, okay? And in this case, it's helpful because your u value is still the x to the 5th minus 6. So then du would be 5x to the 4th, so the 5 helps me in this case, so I would leave it in. But same thing, it's a personal preference thing. Do it however you want. So then this is going to be u to the 3/2, so that won't change. Okay, so then you're going to add and flip. So you're going to multiply this one by 2/5. So then you're looking at 4/75. And you've got u 5/2 plus c. And that is integration by parts.